Uh, so starting, Marcelo Brazil Silka. I'm starting my third year here in Stanford. Now I'm a PhD candidate, and I want to talk about my uh, subject, that is uncertainty analysis of petroleum system models for forecasting the distribution of accumulations. Just a second here. Okay. And I would like to start with a motivation, why to look for uncertainty. And I would like to recall this classical picture from the APG memoir from Murray's, where he integrates the post-mortem analysis of 165 wells. And in the axis, he shows the sequence of exploration wells, and the y-axis, how the volumes in barrels are accumulating. And he plays with the possibility of reordering the drillings. And with that, he shows that changing the strategy for exploration, it's possible to increase the efficiency of drilling with just geophysics, to using geophysics and geochemistry from 28% to 63%. Being 100% of efficiency if all the great volumes were drilling in the very beginning and the dry holes rest at the end, or the other way around, the worst drilling sequence if all the dry wells were drilled in the beginning and then finding the great volumes. One interesting thing about the idea that is behind the work of Murray's is that to go beyond in efficiency, someone has to deal with the uncertainty of the information. What to drill next, or what to drill first. At the time of Murray's, there was no, 1984, there was no way to model the basins. So no physical modeling of the outcomes was possible. Nowadays, it's possible forecasting in, for instance, physical modeling way. But in these, we have uncertainty with the parameterizations for the modeling. And also it's possible in a statistical way, but that's is independent of any physical constraint. So uncertainty is very important to go on. Uncertainty analysis is something that is done in base modeling with Monte Carlo. But traditionally, it's made in a deterministic way where it's created a base model with a careful parameterization. And after that, after this base case, it's make a calibration to find the fine tuning of that. But there's an alternative stochastic way that is based on distributions, and it's not created for calibration. It's created for uncertainty, or for the understanding of uncertainty. And for that, the interactions of the parameters is something that is intrinsic of the construction. And also the likelihood is some operation some measure that is problem driven. It will depend on the idea that you have of the compatibility of models and data. We choose to work with Bayesian evidential learning, the same workflow that I told you about in the beginning of the day, because it starts from uncertainty. And it is a protocol that was organized and published in 2018 by Shade et al. And it's a successful framework with several constructions, several uses in publications. And it comes from the Stanford Center for Earth Research Forecast. It's constructed as a protocol with 6 major steps. Anatoly told about that, but I'm just again organizing my thought. It starts with a decision question that should be addressed, and then the identification of what are the prediction variables for that question, and then some priors for the uncertainty related to that model. And then comes the Monte Carlo with several simulations and falsification of the models that I would like to talk a little more in minutes. Then sensitivity analysis of the parameters and the data and the models. And then design of an uncertainty reduction strategy. To the end, make another falsification and a sensitivity of the posterior results compared to the data from models. Our working data for the research is in CamposBasin in Brazil. In the left, we have a map showing CamposBasin, showing that red square, that is our volume of work. We have also here in this map, the areas shaded in brown is the distribution of the mature portion of the Lagoa Feia source rock, as is presented in the paper of Baglinger et al. 2012. And to the right, we have one picture of the Earth model that we have. It comprises 39 stratigraphic horizons with 5 designed source rock layers and 3 faults inside of that. This Bayesian model was interpreted and assembled by Petrobras, and this cut of 2% of the area of the basin was made available for this research without the kinetics and without the quantitative information about the source rock. The non-petroleum system in CamposBasin is the Lagoa Feia Carapebus, with the source rock here, Lagoa Feia, to the Borremian. And the reservoir rocks, they are a scatter of turbidites that are in between the shales. And the reservoir rocks, they are scattered from the Upper Cretaceous until the Miocene. 11 fields have been discovered in the study area. To the left, I show where they are distributed inside of our volume. and the fields that are painted in the volume of oil initially in place. Together with this 3D vision, I have a plot that is like that one of Murray's, but I don't put in for this the dry wells that's happening. Just to recap, deterministic numerical model of petroleum systems, we all know, but it's important to say it again. They materialize the concepts that were defined by Magoo and Dow in 1994 for the idea of petroleum system. We input the depth horizons that will express the overburden and the chronology that fixes the timing of the system. And then we fill the lithophases that will play the role of the source rock, the reservoir rock, the seal rock. And of course, there are more kinetics and all. But at a time we start to making models, for instance, the model of porosity that we have to address, the model of transformation rate of the kerogen, and to lead to the generation and migration, and we end up with several accumulations. Because of all the uncertainties that we have in those steps in this construction, there are, of course, uncertainties on the output. And the idea of considering the uncertainty on the output, on the accumulations, lead us to customize the Bayesian evidential learning workflow, asking about how to forecast the field size distribution, and together with that, trying to understand the uncertainty of the field size distribution. And we built the uncertainty and Monte Carlo and falsification, sensitivity analysis. I'm just talk about these 4 first steps, the construction of a minimizing of uncertainty, and the posterior of this step, it's future work. So talk about those various steps, starting from the prior uncertainty of the Bayesian model. We must investigate the prior distributions of a model. And for this specific model, as first assumption, we build a table with all the possible parameters to vary. And they were in the number of 46 variables. And the idea was to understand the role of the 5 assigned source rocks, and the quality and station of the source rocks, the age of the source rock, or the effect of the age of the source rock, and also the role of the faults in the secondary migration. 5 of those variables were used to define the drawing of a pod of source rock that is active. Parallel to this construction, that was a construction for investigation, an exploratory point of view, it was constructed a very simple model just considering the Silka source rock and the two variables of TOC and AGI for Silka. And in this presentation, I'm going to show results from this simple model. Another simplification that was used was the very first model had 16 faces that were defined by seismic faces analysis, and they were simplified to 6 faces. It's quite a strong simplification that made the visualization of the patches not so geologic, but one good thing of that is that even with this very simplified model, accumulations still appeared, they were still constructed, and they resemble with reality quite much. For instance, we see here the accumulations that appear in one of the realizations and the vectors of migration at the source rock layer. And this cross-section cut here, where we see the petroleum saturation with one of the accumulations at the top of the maastrichtian appearing. So after we go to Monte Carlo simulation and simulate lots of models, we get into the falsification of the models. And the term is not quite common, but the question arises, what do we mean by falsification? Falsification is a term that comes from the philosopher Karl Popper in 1959, and he was struggling with the idea of demarcation of science. So how to draw a line to specify this is science, this is non-science. And he understood that science does not imply one particular event, one particular data. And also that exceptional data can refute a model. For analogy, it's wrong to create a scientific law, all swans are white, had just seen one white swan. Because at the time that you see one black swan, this general rule, all swans are white, it's broken. From the point of view of a modeler, the idea that is behind the work of Popper is that the spectrum of models must be broad to cover the space of reasonable possibilities. It's like if I'm going to model swans, I must make sure that I have a large spectrum of colors of swans to don't break my general law. And also recalling the famous phrase of George Box that all models are wrong and some models are useful. The falsification applied to a very large set of models, it will attest that this very large set of models is useful for the constructions that come after, because I'm going to have a broad set of models to deal with with all the data that I have at hand and the data that will come after. Uh, to make the falsification, we have to work with quite an easy dimensionality. Geological models have a great value in dimensionality because we have lots of information to deal with. And the way to reduce dimensionality is principal component analysis. We saw uh, four examples today. Just to stress, we used to see principal component analysis or analyze principal components with two plots. The scree plot, where we show the cumulative explained variance of each of the dimensions or each of the principal components, and a score plot that show how the diverse models are scattered uh, and how they related one to the other. In the score plot to the right, we have the models all painted with purple dots, and the data is the red dot here in the middle. Uh, then there's a need of deal with the sensitivity analysis of data in Bayesian models. Uh, because the sensitivity analysis will clarify the dependencies of the parameters. This is a very simple example, but it's very instructive to think about that. The two cross plots to the left, they are the same cross plot of free oil mass related to free gas mass. But the difference between them is that one of them is painted with the values of TOC that were used as initial parameters, and the other is painted with the values of AGI. We can see in the TOC that the graduation of color or, or the increase in TOC is very well related to the free oil mass or the free gas mass in a way that is not so straightforward for the AGI values. With the AGI values, we have this growing from blue to red, more erratic. And this information that is quite visual here can be seen from sensitivity analysis. In this case, I'm plotting here the Pareto plot of this just these parameters. This Pareto plot came from a distance-based generalized sensitivity analysis, and we have a measure of sensitivity in TOC much greater than AGI. This value 1 is a threshold, so they're sensitive in AGI, but it's a greater sensitivity in TOC. Okay. So this plot summarizes the things that we see in the cross plots here. And for a more with more parameters, model with more parameters, it will be easier to use the sensitivity analysis. The next steps is the design of uncertainty reduction strategy. I just would like to say that I intend to use market point processes as representation of the accumulations. And I'm having the idea of, for likelihood, try to compare the mismatch between the GOR distributions of data and model, borrowing an idea of the Hong V from Z-aware. In summary, it's important to have in mind that all the ideas of Magoo and Dow that fundament a Bayesian model, they have to exist in the numerical model, and that also the idea of George Box, that of the usefulness of the model is not just in the choice of which model I need to answer my question, but also when I'm going to a Monte Carlo simulation, it's important to use the falsification to attest the usefulness of the set of models. Also about Bayesian evidential learning, one important thing is that it starts with uncertainty, is not for calibration, it's to understand the uncertainty, and it's an effective framework that have lots of results already published, and it have been using here for construct a meaningful data set for the next steps. With that, I end, and I thank you, all industrial affiliates of BPSM. Thank you. Any question that you have, please?
So I'll take questions from the group. I don't see anything typed into our private chat. So I thought one of the most important things you said on the previous slide, Marcelo, was that Bayesian evidential learning isn't a calibration technique. Mm-hmm. It starts with the uncertainty. And if you could just, we'll have Ken go in a minute because we're running a little bit late. But could you give us a couple of sentences, just hitting that point home that the evidential learning part isn't a calibration technique?
Yeah, well, it can be used by the modeler to calibrate, but it's not a calibration in the sense that I have the result and I'm going to just fix it. It's not a tool to make the fine tuning.
Right. In other words, it has this prior information that you use to define the uncertainty around parameters, and then you try to narrow that distribution at the end of the initial simulations, and then the repeated ones. Yeah.
Yes. Well, also the prior, it's quite important because it must be broad to have all the alternatives that you have at hand and the future alternatives. So your modeling is meant to be real and right.
Yep. Yep.
For all time being.
Yep. Good. Okay. Thank you.
Thank you.
Thanks.